Okay, so the behavior of this system will be described by differential equation. So let's derive this differential equation, okay? And I'll work through this. Okay, so let's work through this. We're just going to go through these steps in a second. And so let's do that. Okay, there you go. All right, let's see. Okay. All right, so we are interested in describing the behavior of this mass attached to the spring. Okay, and if you stretch, so we'll measure distances along that direction, and if when the mass is at that position, the force is given by minus kx. Okay. So force is equal to minus kx. And according to Newton's law, force is mass times acceleration, Newton's second law. Acceleration is second time derivative of the position of this object. So, and so we'll bring this term to the left, m d square x by dt square plus k x xt is equal to 0. And what we'll do is we'll divide this equation by m, so d square xt by dt square plus k over n xt equal to 0. All right. Now, k is positive, m is positive. So just to make sure that there's no confusion, we'll write this as omega squared. So d square xt by dt square plus omega square equal to times xt equal to 0, where omega square was k over m. Okay, so what we have done is this was our system, and the behavior of this system is described by that differential equation. Okay, now there's a couple of things that, well, you learn about solving differential equations and so on and so forth, but the behavior of this system is given by that. Xt is the position of this mass as a function of time. Okay, and we've learned in kinematics that if you know the configuration of a system as a function of time, you can calculate all the properties you want to calculate for that system. So if you can solve for xt, you know where the mass is at all times, and then you can calculate its velocity and its acceleration. Okay. Now here's a couple of things about this differential equation. This differential equation has a second order derivative. So it's called a second order differential equation. Xt is linear, it's to the power 1. And this is all, the second derivative is also to the power of 1. So this is called a linear, it's a second order linear differential equation. Non-linear differential equations are much harder to solve. Anyway, so you learn how to solve these equations. Okay, so again, to summarize, the important thing is to understand that the behavior of a system is modeled by this equation, and generally it's a differential equation. Okay. Now to solve this equation, you learn various techniques. Let's start simple equations. You you solve them by trial and error. You can guess at answers, but as you learn more techniques, you'll become better at guessing answers. So here's the solution to this differential equation. A sine omega t plus phi. Okay, now here's a couple of things about the solution. You see, this solution, there are two constants, A and phi, that didn't appear in this equation. Okay, so it turns out that if the differential equation is a second order differential equation, so if it were a third order differential equation, you'd get three constants that were not in the equation. And these constants are determined by initial conditions. Okay, so in our case, this is the amplitude of oscillation, and this is called the initial phase. Okay, so here's what these would mean. So if this is x equal to 0, and you pull the mass up to there and let it go, this would be the amplitude. So the system would oscillate between these 2 points. Okay, and that would be the amplitude. That would be the interpretation of that. All right, so again, let me summarize. So we were interested in the behavior of this system. Okay, so you wanted to know where the mass was as a function of time, and its coordinate satisfied this differential equation. The behavior of this system was modeled by this differential equation. And you solve this differential equation, and the solution was a sine or cosine. Both will work, omega t plus phi. Okay. How do I know that this is a differential equation? This is a solution. I can plug it in back here and make sure that it satisfies the differential equation. Okay. And I'll let you guys do that. But anyway, now that I know the configuration of the system as a function of time, I can calculate the velocity, which is dx by dt. Okay. And the velocity will be a omega cosine omega t plus p. I can calculate the acceleration as a function of time, which will be dv by dt. And that will be minus a omega squared sine omega t plus p. Okay. So there you go. This one slide summarizes almost the entire chapter. Okay. So the behavior of this system was described by that differential equation. The solution of that differential equation was that. Okay, there's a solution to that differential equation from which we got the velocity and acceleration of the object, which is what we wanted to know. Okay. So, and this is much easier than setting up an experiment in lab and trying to figure all this out. Okay, so that's the general theme. And so that's why you will study a differential equations class, because you will study the behavior of these and then compare the predictions of the model with the actual behavior of the system in a lab. And if your model is not good, then you refine your model. And that's how things go. Okay. Right. So what I'll do is I'll pause now and give you guys a chance to ask questions.